Hey, welcome back to Math with Patrick. Today is January 24th, and you already know we're solving the 24th problem from this Daily Epsilon calendar. All right, let's try it out. How many digits are there in the largest left truncatable prime? Okay, left truncatable prime. What the heck does that even mean? When I read this problem at the start, I had to look it up. Let's first talk about that word truncatable. It comes from the verb truncate. And when you truncate a number, usually it means that you lop off some stuff at the end. So, for example, if I had the number like 12.635, and let's say this 5 just repeats forever, I could truncate this decimal just by lopping off all of these numbers and just calling it 12.6. It's kind of like rounding, although say I had a 7 right here and I still truncated it to the 10th place, I'd still just lop off all these numbers and I wouldn't round up. Because if I rounded this number, it would be 12.7 because this 7 is kind of big, tells me to round up. When I'm truncating a number, it just says cut off all the numbers on the end. Though if we left truncate something, that means we're cutting it off from the left side. So a little strange, but if I left truncated this number, I guess I could cut off the 1, so changing it from 12 point stuff to 2 point stuff. And I guess I could left truncate it kind of wherever I want. Maybe I'd fill in these numbers with some zeros. I'm just kind of assuming here. I haven't really done much left truncating before, this problem actually. Okay, so now we know what truncating looks like. It's just kind of like chopping off some numbers. In this case, we'll be chopping off numbers on the left side of our number. But what is a left truncatable prime? I believe 137 is a nice example for this. So first of all, it's a prime, so I need to prove whether or not this is prime. And the idea of a left truncatable prime is that I could lop off or truncate or cut off the left digit, and I'm supposedly still left with another prime number. So I'd have to check if 37 is prime, and then finally I'd have to check if 7 itself is prime. Well, I mean, that's not really much of a question. At least I know my prime numbers, that I know that 7 is prime, so that's true. Though maybe it's a little bit less obvious that these other two numbers are true. So let's work our way back up. How do we even prove that a number is prime? Well, we need to prove that its only factors are 1 and itself. And as a little note, those need to be distinct. So even though 1 is 1 times 1, 1 and itself are like the same number, 1 isn't prime. So the first prime starts at 2, then we have 3, not 4 because it's divisible by 2, 5, not 6 because it's even, 7, 8, not 9 because it's divisible by 3. Let's see, 11, 13, 17, 19, so on and so forth. And when you're checking if a number is prime or composite, as in not prime, all you really need to do is check divisibility by smaller primes. And even more so, you really only need to check up until the square root of the number you're checking. We did some factoring in a previous video, and so I kind of go over why that square root is the highest you'll ever have to go. I know that root 37 is just above 6. So I really only need to check these prime numbers to determine whether or not 37 itself is prime. Okay, well, it's not even, so that was easy. It doesn't end in a 5 or a 0, so I know that 5 can't divide it. And then there's a little trick with 3s, where if we add the digits of some number and check the divisibility over here, if this number is divisible by 3, then the original one is as well. Or conversely, if it's not divisible by 3, then the original isn't as well. So using that divide by 3 trick, I know that 37 is also prime. And let's just check some primes up until we prove that 137 itself is prime or not. Let's see. A nearby square root for 137 is 12, because 144, well, the square root of that is 12. So the highest prime I'll need to check is this 11. Well, let's just go through that list. It is not even. If I sum the digits, I get an 11, so it's not divisible by 3. It doesn't end in a 5 or a 0, so it's not divisible by 5. And I guess I have to do a little bit of long division for the 7. So let's see, 7 goes into 13 once, do a little bit of subtraction here. 7 goes into 67 9 times, but that's because it's 9 times 7 is 63, not 67. So I'm going to get some remainder from this problem. So 7 doesn't work. And finally, let's just show that 11 is also not going to work. 11 goes into 13 once. Do my little subtraction step. I get a 2. So drop the 7, get a 27. And then 11 goes into 27 2 times. But when I multiply, that's a 22. And then I'm also going to get some remainder here. So wow, that was a lot of work just to show that 137 is a left trunctable prime. I think I'm going to abbreviate that for the rest of the video. I'm just going to call that an LTP. And it has 3 digits. So it took me all of that work to prove that this 3-digit number is an LTP. According to today's problem, or today's date, the answer is 24. And so the largest LTP is going to have 24 digits. That's crazy. That's like 21 more digits than I have here. Like if I don't know, if I tried generating another LTP with 4 digits, I don't know, maybe this number is prime. That's going to be a lot of primes to check. I'd have to check 13 and 17 and 19. I'm not even really sure what the square root of this number is, so I'd have to figure that out to figure out when to stop. Like, this problem is crazy. I don't want to do this by hand. So just to summarize, to prove whether or not a number is an LTP, we need to take the number itself, prove that it's prime, then truncate it from the left or take off that first digit, and then prove that the next number is prime, and keep doing that until we've reached a single digit number that is also a prime. And with this process, all LTPs have to end with a 1-digit prime. So all of my 1-digit primes are going to be 2, 3, 5, and 7. Well, that's it. And as I left truncate it, I'm making it go smaller and smaller. But let's think about it going the other way for a sec, so we can generate some LTPs together. Just kind of by definition, you can't have a 0 in an LTP. It's just kind of because if I could have a 0, then I could just keep adding zeros, as many as I want. And it's a little bit arbitrary when I need to stop or when I can stop. So just kind of by definition, zeros just kind of aren't allowed in an LTP. I noticed something with this too, though. No matter what digit I put in front of it, say it's a 1, say it's anything between 1 and 9, every single time I just get an even number. So this number itself is going to be composite, or just not prime. So I can't tack on any more digits to the left of 2 because, well, none of them are going to be divisible, or they're all going to be divisible by 2. They're all even. So none of them are going to be prime. So 2 is the only LTP that ends in 2. Likewise, the same thing happens to 5. If I put a 1 here, well, 15 is divisible by 5. I put a 7, 75 is divisible by 5. I can't put any other digits onto this 5 for it to be a prime number. So my only candidates are this 3 and the 7. I could do 13 or 23 or 33. Well, that one's composite. That's 3 times 11. 43, 53, 63. Oh, that's another multiple of 3. 73, 83, or not 93. That's another multiple of 3. And then from these LTPs, I could keep making more. So 113 or maybe 213 or 313 could be possible candidates. I guess we could even see, where is this 137 coming from? It would be me sticking a 3 in front of the 7 and then proving that 37 is prime. And then finally sticking a 1 in front of the 37. So now that I know that 137 is an LTP from earlier, I guess I could check some of these candidates for another LTP, but that's going to be a lot of work to do by hand, and I'm not really wanting to prove whether or not a 4-digit number is prime by hand. And this is where coding is going to come into play. This seems to be a very computationally heavy question, and well, I know that robots are better at doing computation than I am. So if I can tell the robot what to do, or the robot being my computer, I'm going to use Python for this example. if I can tell it how to do all these computations for me, it can do those computations real quick, and hopefully I'll be able to generate some LTPs using technology. All right, I wrote some code during the break. I mean, this kind of took me about like a day to make and test. And let me walk through the code, maybe like not line by line, but I at least wanted to explain where everything is coming from. First off, I need to teach my code what a prime number is, and it's going to input some number n, and I'm just assuming that I'll always input an integer in here. If I wanted to be really careful, I would do some tests to convince my code that yes, it's an integer, or maybe like throw some flags, like red flag exceptions. No, this is actually like a word or a decimal number. But anyways, I'm assuming that I'm being smart enough and plugging in only integers to this function. Let's see, if n is 1 or less, return false. So there's no prime numbers 1 or below. Then this case is already covered. So this next one that says if n is 3 or below, or return true, that's just saying like I've already dealt with the ones and below. So really it's only picking up the numbers 2 and 3. This next one is using that modulo operator. This divides my number by 2 and checks if the remainder is 0. I'm also in the same line dividing my number by 3 and checking if that remainder is 0. This is just checking if my number is even or a multiple of 3. If it's either one, or maybe it's both. So if the number 6 would flag both of these, and it would return false because it's divisible by 2 and also divisible by 3. Then finally, I should, or like I could rather, just only ask my code to divide by primes, kind of like how I was doing on the whiteboard earlier. But this function itself is testing whether numbers are prime, so it would be a little bit silly to use my function in my function to generate primes to divide by. Instead, I'm choosing a group of numbers that is probably prime. I'm starting at 5, which I mean is prime. And then I have this while loop. So it's going to keep on incrementing over and over again. And at the end of my while loop, it's going to increase my I value by 6. So it's going to start at 5, then 11, then 17, then 23. It's just adding 6 every time. But all of the numbers I just said were all primes. And it's testing if the number I'm inputting is divisible by 5, then 11, then 17, then 23, then 29, and so on. Finally, it does hit 35, which is composite. So it's a little silly to test 35 here. But again, it's hard for me to tell my code what primes to divide by if it doesn't already know what a prime is yet. I'm also testing another divisibility rule here. You can kind of think of this as me adding 2 to my I value and testing that. So while I'm testing whether or not it's divisible by 5, I'm also testing divisibility by 7. While I'm testing 11, I'm also testing 13 at the same time. So I'm essentially doing pairs of numbers that are 2 apart. And if any of these odd numbers, all the way up until the square root of n, if any of these flag as divisible by that number, then it's going to return false. If I test all those numbers and all of them, not like they don't work, then finally I'll return true. This number is indeed prime. There are no numbers that I was able to find that divide this number. It's going to take a long time to do this for really, really big numbers, but it does check all the possible like ways that a number could be prime. So this one will work every time. Now I wrote some code to prove whether or not something is a left trunctable prime. And this one actually is a recursive function. I'm going to call this function in itself later, and this time it'll make sense. So if it is one of my 1-digit primes, 2, 3, 5, or 7, I'll return true. Yes, all of those are left trunctable primes, or LTPs. If a 0 is in the number, and here I'm converting my number into like a string or a word, it's just a little bit easier to search for characters in words rather than digits in integers, as far as I'm aware. Anyways, if a 0 is in my number, return false. I can't have an LTP with 0 in it. Here's the weird part. I am calling the function in itself, and I have some really weird code happening right here. Let's see. So here I'm turning my number back into that word. So it's not considered a number in my code, but rather like a string of digits. This part is a really concise bit of code that says, take my whole word cut off the first digit and give me the rest of it. So this whole chunk is cutting off that first digit or truncating it from the left. And then here I'm telling my code to turn it back into an integer. And then finally, I'm asking, hey, is this new integer where I take off the first digit prime? And I will then test the smaller value. And so it's going to go right back up to the start. It'll test if it's a 2, 3, 5, or 7. It's going to, well, it probably won't have a 0 in it this time. And then it's going to go right back into here. And so I'll keep truncating it over and over and over again, all the way until I get one digit left. And then finally, it'll tell me whether or not it's prime. I do have this is prime condition in the middle. So it is possible that I keep truncating it from the left over and over again. And then eventually I hit some composite number along the way. And then it'll skip down to this else part in my code and it'll return false. So this one checks if I have a left truncable prime or not, LTP. Okay, finally, I wanted to generate some of them. I want to start with my 1-digit LTPs. And I'm going to do a while loop. And this is just going to be growing and growing my list of LTPs. I'm going to find some new ones. Currently, I have a list of none of them, so I'll be like putting them in that list. This CTR is just a counter, and I'm just going to be counting how many new LTPs I find. I'm going to choose digits between 1 and 9. I know it looks like it says up to 10, but these ranges stop right before this number. So I'm deciding to put digits 1 through 9. And for all of my previous LTPs, currently it's just 2 through 7, I am going to add that new digit onto the old LTP. So the very, very first number that this will create is a 12, because it's the first digit D here in the first LTP in my previous LTP list. And then it'll check if this new number is prime, then add it to my list of new LTPs. Then, of course, 12 isn't prime, and so this 12 will go back into this code here. It'll check if 12 is prime, 12 isn't, and then it will detect that it's not, and so it won't add a new LTP to my list. It won't add 12. So then it'll go back. It'll try putting a 2, the digit 2, in front of this 2, and of course it won't work for any of these 2s. Then it'll try adding 13 as the next LTP, because the digit cycles back down to 1, and it picks this to concatenate or add the 1 to. And then finally, it will detect that 13 is prime. I will add 13 as my new LTP into my new list of LTPs, and I'll increase my counter by 1 just to keep track that I do have a new LTP. Eventually, I find all of my 2-digit LTPs, and I'll add them to my original list. And then I want to print out my LTPs and just figure out, like, what do they look like? Eventually, I'll create 2-digit LTPs, then 3, then 4, then 5, and I'll keep cycling all the way until this counter hits 0. That's when I don't find any new LTPs. Like, I've tried all the digits 1 through 10, I've tried them on all previous LTPs I generated, and I don't find any new ones. And at that point, I will have found the biggest. All right, well, let's hit run and see what happens. I'm going to generate a list of LTPs. Wow, okay, so it generates all of my 1 and then 2-digit LTPs like immediately. And then now you can see that it has all these 3-digit LTPs. Looks like that caps off at 997. The next list also contains all the 4-digit LTPs, and that's a whole bunch. Wow, it's just, there we go. We end here. And as I've just been rambling on, we have a list with 5 digits, 6, 7, 8, 9, 10, 11, 12. So this 13-digit LTPs, these ones are going to be hiding at the very end. Where are they? There they are. And so now I have 13-digit LTPs already in my code. I think if I wait patiently, then I'll get a list of 14-digit LTPs in like just a sec. But, well, here's the problem though. Today's date's the 24th. There's going to be a 24-digit LTP at the very, very end of my very, very last list. And I'm still waiting for, there they are. Finally, I have my 14-digit LTPs. That kind of took a while to wait for. So this is my largest 14-digit LTP. And now I'm stuck waiting for the list of 15-digit ones. And the bad part of this is that confirming whether or not a number is prime takes a long time. Like this is the part of the code that's taking the longest. Is I'm walking through all these numbers and I'm continuously checking whether or not these numbers are prime, and it is really computationally intense to determine whether or not a number is prime. This is actually kind of like the basis of cryptography. Is that it's really hard to factor very large numbers. It takes a long time, even for computers. And I'm still waiting for my list of 15-digit LTPs. It's going to take forever. So, well, not forever. It's probably going to take hours. And I mean, I could have this run overnight, but I don't know if you want to sit here and wait. There they are. Oh, okay. The list of 15-digit LTPs just showed up. There's my 15-digit, largest 15-digit LTP. I'm just going to count them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, 15 digits. I don't want to wait for 24. So there is one more thing I want to show you, and it's how to speed up the process of searching for a prime. So like all good coders out there, I took code from somebody else. I'm serious. Like this is kind of how you start to learn how to code. Um, I looked up something on Stack Overflow, and I was asking how to quickly figure out if a number is prime. And there are these primality tests. This is called the Miller-Rabin primality test. And the idea is that this test is pretty sure that a number is prime, but it doesn't prove it in the same way that like my code did at the start. Um, the idea behind a probabilistic primality test is that prime numbers all have some features in common. Like, okay, besides 2, like they're all odd, and they're all one number away from a multiple of 6. Again, besides like the low ones. So like 5 and 7 are near 6. 11 and 13 are nearby 12. The prime number 29 and 31 are also both near 30. So prime numbers have certain things in common, and for some reason, just computationally, it's easier to check if these really, really big numbers also have these similar features, um, similar to prime numbers. And it's not necessarily proving that they are prime, but they're just so close to being prime. They have all the same features that you can be pretty sure that they're prime. And the way that this Miller-Rabin primality test works, I don't actually completely understand it, but I do know that, let's see, I was using this code. So I did bring this code into mine, and I edited it a little bit just to match my own. But you can choose, there we go. You can choose this value of k, and it will test this, the Miller-Rabin test, k number of times. And the more times you do it, the more accurate you'll be. Because if we go into the Miller-Rabin test, this code right here picks a random number that is 2 or greater, and basically choosing this different number each time as your base number, you are asking if this base number is helping give you more evidence whether or not this number is prime. I was looking this up a little bit. Apparently, each number has about like a 75% accuracy rate at least. And so if you try one trial, you might be wrong. But if you try like 10 different trials, well, there's a really slim chance that you're wrong. So if I make this k like say 50 or even 100, that's like the chance of failure is essentially 1/4 to the power of this k. So if I make it sufficiently big, then I'm almost certain that this test will give me only prime numbers. And I use this code in mine, and let me move back over to the Python code that I wrote. Alrighty, so here's a new file where I have that Miller-Rabin test included. And you know what? Let me actually do something kind of goofy. I want to just do one test, as in something not very accurate. And when I generate these LTPs, I'm going to ask my code to print out the length of the LTPs. And I'm going to run my code over and over again just to see if this length is going to be different. And if it's different every time, that tells me that my code is accidentally including some non-prime numbers or forgetting about others. So let's see what happens when I generate this list of LTPs and finally print out that ending length. So let's hit run. And as you can see, that was like nearly instant. I just got a list of 4,317 LTPs. And you can also tell that these first few ones are exactly the same as what we saw earlier from my other file, the one that definitely was right about generating prime numbers. And I don't really remember what the list was doing after that, but I do recognize all of these ones, and they're definitely all primes. And I got 4,317. Well, if I try running that again, now I get 4,261. Okay, so I really need to increase the accuracy of my Miller-Rabin test because I'm getting different values each time. So let me try maybe 50 trials, and let's see if that makes it consistent. This should make my code run a little bit slower. Yeah, okay, it took like, what, 2 seconds instead of half a second, and I get 4,260. Let's just run it again. 4,260. Let me run it again just to be sure. Okay. And that's so quick, honestly. Why not just do like 200 trials just to be super accurate? It's going to be a bit slower. Like now you can kind of tell that it's taking a bit longer or more of a while to get through all those computations, but it seems like this is this number that I'm settling on. I think I have exactly 4,260 LTPs. Let's find the biggest one. I'll scroll all the way over here and I'll grab this one. I'll hit copy on my keyboard. And I already have this like testing function over here. And so let me test if this is actually an LTP. This little hashtag is turning that into comment code, so I don't run that code again. And then, what was it again? It was, left trunk prime, and I'm going to stick that number in there. And I should get, let's see, it'll just return true. So let's see, what happens if I hit run? Yeah, nothing happened. I want to print the output of this, and I really hope that it prints true. Hey, there we go. Okay, so my code just told me that this indeed is a left truncable prime. Well, it's probably one because I'm using that Miller-Rabin test, but I have so many trials here, like 200 trials. Let's see what happens if I make it 2,000. Yeah, okay. I am so certain that I have found an LTP, and this is the one. And if you're just curious to see what would happen if I tried it in my previous code, the one with that slower prime checking function, let me make sure I'm not generating all those LTPs again. And I try figuring out if this one is an LTP or not. It's just waiting. I think this would take about 8 to 10 hours is my guess. I tried doing some calculations about like how long these computations would take. I have no idea. Ultimately, I do need this Miller-Rabin test because otherwise my code is just way too slow. So there it is. That is the biggest LTP. Let me generate that list one more time because I keep generating them and my code just eventually stops when I don't generate any new ones. Oh, and it's kind of slow because I gave it 2,000 trials each time. Let me make it that 50 again. 50 seemed accurate enough. There we go. Cool. Yeah. Same length of a list, so I'm pretty sure I found them all. Still a true. So this is my longest LTP. And then let's see. I could count the digits by hand, but I'm already coding. So let me find the length of the string of that LTP. This should give me a 24 right after that word true. So let me print out that number. There's my LTPs all again. That's the number of them I found. True, it is an LTP, and there it is. It has 24 digits. All right. Whew. Well, thanks for coming along. This was a very, very long episode. I'm happy that you watched either some or all of it. And thanks for coming along for this ride. Wait, one more thing. I do want to plug the OEIS. This is the online encyclopedia of integer sequences. And if you're ever working with a fun, funky sequence of whole numbers or integers, you can usually find that list here. And typically the lists only go up so high on this first page, but once you like scroll down into these links, you can usually find more information about it. So I was already looking at this link a lot during my work in making this video, just so I could be sure that the numbers I was getting were indeed LTPs, because I was using that probabilistic Miller-Rabin test. So I just wanted to make sure that I was accurate, and I cross-referenced it with the OEIS list here. So as you can tell, we do have 4,260 LTPs, and this is the number that I found at the end of my video. It does have 24 digits. So here is just some added confidence that my code found the largest LTP, and it counted up these 24 digits perfectly. Okay, See you tomorrow for realsies. Bye.